So if I asked you to calculate the square root of 65 without a calculator, what would you tell me? What would you guess? 8 point something, right? Because square root of 65 is close to the square root of 64, and we know what the square root of 64 is. So 8 something is a good guess. Now, we're going to kind of build on that idea a little bit. That is, sometimes what we know about the value of a function at one point helps us understand the value of a function at another point. So let me label some things on this graph here. Here's y equals f of x. That's some function, deliberately not labeling what it is. And let's call this point x near 2. And then this would be f of x. So we got a point here. This line is the tangent line. It's tangent at that point x. We're going to examine this function at a point here and then a nearby point. So just a minute ago, I asked us to calculate the square root of 65, and we referenced the square root of 64 because square root of 64 is a comfortable point, a point that we know. But we can use a point that we know to kind of reach out and try and get some more information about nearby points. So let's move a little bit to the right here. And I'm going to go an exaggerated amount. Typically you go something that's pretty close. I'm going to call that delta x, that distance. So this next point is going to be x plus delta x. It's going to be over here someplace. And let's look at the value of the function now. Well, that'd be up here. And then over here. So someplace here on the y-axis, you're going to have f of x plus delta x. Okay, so that's how much the function has changed. And let's look at it a different way. So this distance here is what's called delta x. Delta typically stands for change in. You'll see it in economics, you'll see it in physics, the change in your net income or the change in the velocity, etc. So this distance is delta x, change in x. What do you think I could call this distance, or equivalently this distance? Change in y, delta y. So that's your delta y. And delta y actually has an expression. Delta y is just the difference in these two heights. It's this minus this. This is going to be the exact change in the function. And that definition is down here. Delta y is f of x plus delta x minus f of x. So it's the exact change in the function. When you go from one point, say the square root of 65, to the square root of 64, how much has the value of the function changed? What else can I tell you about this? Well, let's define delta x. Delta x is also going to be known by another name that's a little bit familiar to you. It's called dx. That's the differential. And dx and delta x are interchangeable. So dx and delta x are interchangeable. Well, it's time to introduce the tangent line into the discussion and understand a little bit about what's going on with the tangent line. So this is our tangent line. What's the slope of the tangent line? How do you measure the slope? What tells you about the slope of the tangent line? Derivative, good. So in working with the derivative, we notice that this tangent line, for small values of delta x, when we're pretty close to our original value of x, the tangent line is actually pretty close to the function, especially if you're really close to this point of x. So what's the tangent line? Well, let's see. We got y prime is the equivalent to f prime of x. We also go with another notation. It's dy by dx. So let me move over here a little bit and discuss this derivative notation. Of course, this derivative notation goes back to Leibniz. dy by dx is f prime of x. But I actually know what dx is. Dx is just delta x. So let's take this equation and multiply both sides of it by dx. What's going to happen on the left-hand side? You're going to get some cancellation here, right? dy, and on the right-hand side it's just going to be f prime of x dx. So that's actually an easy problem and an easy calculation here for us. Should be some easy problems for your exam. Basically, it's just an excuse to ask you to differentiate and remember one extra little thing about this. So let me take a pause from this discussion and let's do a couple easy problems that relate to this, just to kind of get used to what this is. Then we'll come back and further understand what this means here. But for the moment, let's take a look at problem number 16. Y is the square root of x plus 1 over the square root of x. You're going to be asked to find dy in this example. It might help to rewrite this as x to the 1/2 plus x to the negative 1/2. If I differentiate both sides of this with respect to x, on the left-hand side I get dy by dx. On the right-hand side, I'm hoping this is going to be pretty easy because it's just polynomial type terms. So bring down the exponent, subtract 1 from the exponent. We get something like this. I'm not worried about cleaning this up. All I'm interested in is calculating dy. And keep in mind that that's what our goal is to find dy. Well, there's one last step to do. Does anyone know what it is? Yeah, multiply by dx. So if I multiply both sides by dx, then on the left-hand side, I get the dx's to cancel out, so I get dy. And on the right-hand side, well, I just get this. So, wow, there's dy. There's your expression for dy.
That was easy.
Yeah, cool. That's it. That's all there is to it. So on the test, if I ask you to find dy, basically it's just a big excuse to ask you to calculate a derivative. Now there is an extra point. Make sure that you get that dx on the right-hand side there. But that's it. That's all I'm asking for when I'm asking you to calculate dy. Let's do another calculation like that, and then we'll go back and understand what dy actually represents. Now the second example I chose because sometimes you struggle a little bit with some of this notation from trig. So let's take a look at problem number 20. Y equals the secant squared of x divided by 1 plus x squared. It may help us to recall that secant squared of x, that notation really means that the squared function is on the outside. In other words, it's the secant of x quantity squared. What rule do we have to use in differentiating this? Chain rule, what else? Quotient rule, all right? So let's start out using the quotient rule. I get dy by dx. And let me give myself a fair amount of room here. Personally, I like to start in the denominator. What should I do to start with the denominator? There you go, square it. So square the denominator, and then the denominator again, 1 plus x squared times the derivative of the numerator. Now let's use this second form to differentiate the numerator. What's the outside function in this case? The squared function. So it's going to be 2 times the secant of x to the first power times the derivative of the inside. What's the derivative of the secant? Not co. Secant x, tangent x. Thanks, Khalif. So secant x tangent of x minus the derivative of the denominator times the numerator. So it's going to be 2x times the numerator times secant squared. Nice. Let's clean this up just a little bit. But are we okay with our application of the quotient rule? Good there so far? Okay. To clean this up a little bit, let me notice that if I distribute this, or if I multiply this, I'll have a secant times a secant. In other words, a secant squared. So there's a secant squared in common with both of these. What else is in common to both of these? A 2. So let me factor out the 2 secant squared of x. That's going to leave behind 1 plus x squared times the tangent of x minus just x, I guess, right? Is that right? Yeah, because the 2's gone out and the secant squared's gone. Yeah, so minus x. Beautiful. And we'll leave the denominator factored as is. 1 plus x squared squared. Now, it's certainly understandable and very easy after all this work to just pound your chest, declare victory, and go home. Mission accomplished, right? Not quite. Remember, you're asked to solve for dy. So that one little extra point here on a problem like this is to multiply both sides by dx and write this as 2 secant squared of x times this whole numerator divided by tangent, or excuse me, divided by 1 plus x squared squared, tangent of x minus x, times dx. So just put that dx term on the right-hand side when you're all done. Now you can declare victory. Back to our question then. Well, what is that dy? What does this dy represent then? That's a good question. Let me give you a good answer here. Dy is not going to be the exact change in the function. That was delta y. Dy is going to be the approximate change in the function as measured by the tangent line. So this is dy. It's how much, not does the function change, but how much does the tangent line change. So dy is the approximate change in the function. And let's just do this. Dy, and make that an equals, not an approximately equals, because dy is defined as f prime of x times dx, and that's the approximate change in the function. How does that help me out? Well, it's going to give me a different way to do approximations. It's going to give me a different way to approximate things like the square root of 65. And let me show you where we're going to get a different approach to that. It's going to start out with this, which is delta y is f of x plus delta x minus f of x. And I'm going to rearrange this a little bit. I'm going to move this f of x to the other side. So we'll call it f of x plus delta y equals f of x plus delta x. Now this is still an exact relationship. All I did is I moved one term to the other side. Not a big deal. But what I can do now is realize that delta y, which is an exact expression, can be approximated by dy. dy is pretty close to delta y, as long as this distance here isn't too big. So our new point, f of x plus delta x, can be approximated by f of x plus f prime of x dx. Or in other words, f of x plus dy is approximately our new point. So it's these last two relationships that we need to study and understand a little bit. And I think I'm going to reverse things up a little bit, and we'll do problems 42 and 44 to start with. Okay, so let's start with problem number 42. And then we'll kind of go back and look more at our handout and try and understand a little bit more about our handout. So problem 42 asks you for the cube root of 26. Boy, that's close to being an easy problem, right? What number would I put under there to be the easy problem? Cube root of 27, right? Cube root of 27 would be easy, it'd be 3. But that's not what we're given. So let's take a little bit of a step back and realize that the function I'm dealing with here is f of x is the cube root of x, or better yet, x to the 1/3 power. Now I want to find the cube root of 26. But I don't want to take out a calculator and get an exact value. We're not going to necessarily refer to a calculator in doing this problem. So instead what I'll do is I'll use this relationship that f of x plus delta x is approximately f of x plus dy. Or you could also write it as f of x plus f prime of x dx. So that's your differential. It's how much the tangent line changes. So this is a good approximation. Now what do I know here from this? I know that x plus delta x is 26. But you told me just a minute ago that the one that you would want to evaluate is when x equals 27. What does that mean delta x has to be? How big of a step are we making? Be very precise though. 27 plus 1 would be 28. Negative 1. So that means that delta x is negative 1. It also means that dx is negative 1, because dx and delta x are the same thing. So how does that help me here? Well, f of 26, which would be the square root of 26, is the same thing as f of 27 plus negative 1, which is approximately, well, here's my x, here's my delta x, or dx. It's approximately f of 27 plus f prime of 27 times negative 1. There's only one thing that I'm missing in order to complete this calculation. Can anyone see what I'm missing in order to complete that calculation? Yeah, I need the derivative. Okay, so let's come back up here. F of x is x to the 1/3. What's f prime of x going to equal? One-third x to the negative 2/3, right? So I think I've got everything that I need to plug in this formula. F of 27 is going to be the cube root of 27 plus f prime of 27. Well, that's going to be 1/3 times 27 to the negative 2/3 power times dx, which is negative 1. All right. Cube root of 27 is 3, so that makes sense. The cube root of 26 is going to be something close to 3. Not going to be exactly 3, but it's going to be close to 3. This is going to be 1/3 times, that's going to be 1 over 9 times negative 1. In other words, 3 minus 1/27, or 2 and 26 divided by 27. So that's our approximation to the cube root of 26. How good we do? Is that a good approximation? Let's find out. Take out your calculators. Let's see. One of the things that I'm going to want you to calculate is something called the relative percent error. But first of all, let's just kind of do a little bit of a comparison here. You can find the cube root underneath the math button. So if you hit the math button, I believe it's the fourth option down, math 4, cube root of 26, that's the exact answer. How about our approximate answer? Well, our approximate answer was 2 plus 26 divided by 27. How well do we do? Do those answers look pretty close? Considering that the second one was really just a couple of fractions, yeah, I think the second one is pretty close. Exactly how close is it? Well, let's figure that out. The relative percent error. You can calculate that this way. You take the true value minus the approximation and divide it by the true value. So you're going to compare the error to the true value. Now, I don't like taking the absolute value because that robs me of some information, but this is probably more of a standard way that you're going to see it calculated. The absolute value of that times 100%. Our true value was this one up here, the first one, right? So here's what I'll do, just to make my life a little bit easier. I'm going to take the cube root of 26 and store it in x. Now I want to compare the true value to my approximate value. So I can do that this way. I'll take parentheses x minus, let's see, how do I want to do this? X minus x minus 2 and 26 over 27, that's the approximate value. How do I want to enter that? You can do it this way. 2 plus 26 divided by 27. So the true value minus the approximate value divided by the true value. So what should I be dividing by here? X. And then times by 100. That converts that decimal value that you're going to get into a percentage. So, wow. That's amazingly good. That's less than 0.02% off in terms of our calculation, in terms of relative error. So the relative error in this case is approximately 0.0157%. So less than 0.02%. That's really, really good considering the little work that we did. Okay. How are we looking on 42 there? Yes? I could. Yeah, that's something I like to know, and we'll do another example or two like that. Yes?
There was a part where you started plugging in for F27 and F prime 27 with some other numbers.
Well, F would refer to this, and then F prime goes back to this. So that's exactly what I did when I calculated f of 27, I put it into this function. And then when I calculated f prime of 27, it went into that function. Charles?
Ryan, do you want us, or how do you want us to write the answer for both? Or is it like equals that approximate?
You know, I rounded this off. You know, it's a good question. Is it approximately? I think probably the approximate is better here. So in case you're not up to speed on this, when you draw an equal sign, which is kind of squiggly, that means approximately, not necessarily exactly. So this equals this, that's exact. This is an approximation because I cut it off after a few decimal digits. So it's approximately, I guess. I'm not going to mark you down if you use the wrong one. Yes?
Was the answer on the calculator negative? Or did
Yeah, the answer on the calculator is negative, but when you take the absolute value of it, that's when it becomes positive. So that's why I didn't write down the negative. I do like having the sign here because that tells me if my approximation was bigger than the true value or smaller than the true value. But like I said, many books just take the absolute value of that. They don't look at above or below. Let's try another one like that. Then we're going to go back and look at the handout a little bit more. It's problem number 44. This time you're going to have to be a little bit more engaged in helping me through this. We're asked to calculate 2.99 to the third power. So I wouldn't mind getting away from the threes and something like this. If you had to guess 2.99 to the third power, if you just had to guess, what would that equal? Yeah, 26 something, right? Almost 27, right? Because you're looking at that going, well, the function we're really dealing with is f of x equals x cubed. And boy, that's close to, it's not exactly, but it's close to 3. And 3 cubed is 27, so it should be a little bit less, 26 something. Sounds like a good answer. From our last problem, I know I'm going to need the derivatives, so let me put that down here. F prime of x is going to be 3x squared. And then this next idea that we've used a couple times, or at least introduced and used it once, is that f of x plus delta x is approximately f of x plus f prime of x dx. You have to have this one memorized. This here is your dy, your differential with respect to y. It's the change in the tangent line. But it gives us a means to approximate functions with a nice little, linear approximation here. Let's take a look at what we've got. We want f of 2.99. Now 2.99 is really close to a nice convenient point. F of 2.99 is really f of 3.00 plus what number? Good. So that becomes, this becomes your x, and I didn't have to write 3.00. I think I might have done that because there's a decimal here. There's your x, and here's your delta x right there. X is 3, delta x is negative 0.1. The rest of this stuff we can fill in according to this formula. This is approximately something here plus something here times delta x. See how far you can get with this stuff. Kind of lined it up for you a little bit. See what you can do. So fill these things in from our formula. calculate the relative percent error. This is f of x. So here's your x. Really should be f of 3. F prime of 3. And then delta x is negative point. She's just putting 3 here and here. That's what x is, right? X is 3. Okay. This is right. Because 3 cubed is 27. You end up with 27 times negative 0.1. You end up with 27 minus 0.27. Should be 26.3. Okay. Just round it up. Except the square should be with 3. That would be 3x squared is your square root. Alright, so plug in 3 to get rid of here.
What do you put the question there?
That's f of x. So x was 3. So you should be, f of 3. So you should be 3 here, 3 here.
Oh yeah.
And those values go into roots. Alright, well, f of x cubed would be x to the 9th. Right? So this is saying something
Okay,
interesting.
I take the f of the space from okay, is this like
Look at that, Sean. Oh, that's exactly
but
right.
I know you're gonna do another constant and you just plug that
Scotch?
oh yeah, you divided by the true value, not by I don't know why I did that. Yeah, just take that. Just do what I did, but do it with like the right value.
And then you can calculate the relative percent error. Now, the truth is, okay, so let's see how this one works. I need to plug in x into both of these, and then delta x, which of course is your dx here. So plugging those all in, f of 3, f prime of 3, negative 0.01. F of 3 is 3 cubed, plus 3 times 3 squared, times negative 0.01. So this equals this, which equals 27 minus 0.27, which is 26.73. So that's our estimated value. It's an estimate because we have an approximate sign here. That's approximately what f of 2.99 is. How close did we come? Let's calculate the true value and compare it. So the true value would be 2.99 raised to the third power. Get some awful number like that. And if I want, let's store that in x. I'll take parentheses x minus 26.73 divided by x times by 100. Wow, that's a really, really small relative percent error. That's less than, that's about 1/3 of 1/100th of a percent off. That's really, really good. So, great estimate there for us. So the relative percent and percent error is about 0.00336%. That's really, really small. Okay. So you're seeing how the differential here, and this term here is our differential, it's our dy, can be used to help us approximate functions. Let's go back and appreciate one more thing about the differential, and then we'll finish up with a couple last problems. So let's take out our handout. Is there any other comments or thoughts on problem 44 here? Okay. So what we're going to do is look at the back side of this now and understand something about how well our approximations perform as this value delta x gets smaller and smaller. We're going to work with this function, y equals the square root of x, and we're going to approximate this function near x equal 1. So let me graph this and give you a nice graphical display about what we're doing. I'm just going to draw a rough and exaggerated graph of the square root function. So it's going to be a parabola that opens sideways. It's going to be the top half of that. And we'll look at it near x equal 1. So near x equal 1, or at x equal 1, y equals the square root of 1 is 1. Square root of 1 is 1. But what happens if we were to move a little bit of ways away from 1? So say at 1.1 or 1.01. Well, you know, square root of 1.01, and even maybe to a lesser extent square root of 1.1, can be approximated if we use the tangent line. So filling in some numbers here, let's go with this one. At 1.01, this is going to be f of 1.01, or the square root of 1.01. This difference is the exact change in the function. That's how much it increases by as you move this distance. This distance here is your dx or delta x, the distance between these 2 points. This distance is your delta y. That's exactly how much the function changed by. You know what? I drew this point on the wrong curve. It should have been here. We're going to use that point in a minute anyways, but that should be the square root of 1.01. It's this much, which is your delta y, the exact change in the function, which would be the square root of 1.01 minus the square root of 1. Let's see how well it does. Let's see how well the differential does in approximating that. It is our dy term. dy for this problem can be calculated from up above. Here's the derivative. You can rewrite the derivative this way. Here's another repeat of problem number 16. If I've got the derivative, what's dy? Yeah, it's it's 1 over 2 square roots of x times dx. Basically just multiply both sides of this equation by dx. You could also write that dx right on top here. You could write it as dx over 2 square roots of x. That's the approximate change in the function. In fact, if you want, you can write that right in here. Dx over 2 square roots of x. Let's use that to fill in the rest of this table then. So if I start out at 1 and I want to calculate the square root, if I start out at 1, I want to calculate the square root at 1.01, that is my x plus delta x, well, then I'm going to cause the function to change a little bit. How much is it going to change? Well, f of 1, which is up here, f of 1 is 1. The difference between the function at an old point and the function at a new point is my delta y. Square root of 1.01 minus 1. Let's figure that out. Square root of 1.01 minus 1. I get 0.00498. What's dy going to be? So this is the exact change in the function. What's dy going to equal for us in this case? Well, 2 with the square root of 1. What's dx at this point? Good. It's going to be 0.01. Remember, dx equals delta x. So 0.01 divided by 2 is going to be 0.005. So this is the exact change in the function. That's the approximate change in the function. That's pretty good. The difference between these two is about 0.00040 zeros and then a 1, 2 according to what we have here. The relative percent error has gone down to a mere smidge. So keeping the signs there, not dropping them, 0.261%. What that's saying is that as you get closer and closer to 1, the differential here is a better and better approximation of the actual function. And you can see that as these values, if you go from 2 to 1.5 to 1.1 to 1.01, as you get closer to this point, then this line, the tangent line, is going to be a better and better approximation to this point. Okay, let's finish up with 2 more problems. Problem number 30 and then 34. So problem number 30, before we get going with that, let me talk a little bit about the area formula involved here. So area of a circle has what formula? Pi r squared. Okay. What if I was to differentiate this with respect to r? dA by dr. What am I going to get? Yeah, 2 pi r. But you're right in noticing that it's the circumference. So if you think about what's happening, suppose you had a situation in which the radius of this circle was increasing. Maybe it's an oil spill or something like that. But if the radius of this is increasing, how is it increasing? Where is it increasing? That increase is going to take place at the boundary of your circle, which is exactly what this is. It's the boundary of the circle. That's where the change would take place. So that's your derivative. If I multiply both sides by a dr, I get 2 pi r dr. Okay, that's nice. But what's that mean? Any takers? What's that going to tell me? Yeah, that's the approximate change in the function if you change your value of r. So let's actually read the problem here now and take a look at what they're asking. Section. There we go. So the measurement of the radius of the circle is 16 inches with a possible error of a 1/4 inch. Use differentials to approximate the possible propagated error in computing the area of the circle. Well, if the actual radius was 16 1/4 inches as opposed to 16 inches, how much could you be off by? What's the possible error that you could make? Now, in a problem like this, because the formula is pretty simple, it's not too hard to calculate the exact error. But this is, right here, your differential is the possible propagated error. Now, they told us at the start of this that the radius of this circle was 16 inches. What was the error that they mentioned? Good, and that 1/4 inch is your dr term. So I think we've got pretty much everything we need in order to calculate the possible error, at least an approximate version of the possible error. So it's going to be 2 times pi times 16 times 1/4, a 1/4 of an inch. So that's going to give you 8 pi as your possible propagated error. Okay, not bad. Let's see if we can't figure out the exact error. Now, the possible propagated error just comes from the differential. The exact error, let me rewrite this way. Let's call this A of r. So the area depending on the radius. So the exact error is going to come from this. It's going to be delta A. It's going to equal the value of the function at 16 1/4 minus the value of the function at 16. So that's going to be pi times 16.25 squared minus pi times 16 squared. Let's take out our calculators to get a couple numbers here. 16.25 squared is 264.0625. 16 squared is 256. If I subtract these, I get the exact error is 8.0625 pi. So that's the exact error in the calculation of the area if you had the wrong radius. How does that compare to the real error? Or the estimated error. Here's the exact, here's the possible. How do these compare? Are they pretty close? Why don't you take a moment and see if you can't calculate the relative percent error. Now when you do your true minus approximate divided by the true, the pi's are going to all divide out because there's pi's in all these. So you can just do it with the 8 and the 8.0625. It's up to you. But see what you can do in terms of calculating that error. So for myself, it looks like this. True minus the approximate divided by the true times 100%. So I'm getting a little bit less than 1%, about 0.775% relative error. So approximately 0.775% relative error. Yes, sir.
I feel like we're getting closer to understanding that RDRR.
Yeah, yeah. That's
I didn't understand it when you showed it at first, but I think we're getting.
yeah. You can go back and look at that Simpsons joke now. Remember the RDRR joke? Should we pull it up real quick?
Yeah.
All right. Let's see here. So just new tab. Simpsons RDRR. Okay. Yeah, it's just. Let me